Hello and welcome to today's tutorial session. In today's lessons, we will talk about transmission line theory, and under transmission line theory, we will look at transmission line equations, or how they proved the transmission line equations that we have. Before we begin, let's take into consideration this L, R, C, and G, and these are called primary constants, right? And these primary constants are just small sections taken out of the transmission line. What I mean is that if I take L, for instance, it means that the units for L will be Henry per meter. That is a small section of the transmission line has been taken over here. If I take R, R will be ohms per meter. That is a very small section of the transmission line. The same thing happens to C. For C, we will have farad per meter, right? But under transmission line theory, what we want is that we want the absolute value for L, R, C, and G. So if you want the absolute value for these, you have to just multiply this by M, so that if this M cancels the M over here, we will have H. That is an absolute value for L. The same thing will happen to the resistor over here. So like that, we have to multiply everything by M to cancel out the M's, and we'll have the absolute value for each primary constant. So what will happen is that we will take a small section, or you multiply all the primary constants by section delta x, and these is just M, right? A very small section of the transmission line, right? So what will happen is that if, for example, I apply a voltage V here at the input of the transmission line, there will be a current I flowing this side, right? And this current will appear at the output, and this current will be I plus a certain, and this current will be I plus a certain delta I. The voltage that will appear here will also be V plus a certain delta V. This is because if I apply a voltage at the input of this transmission line, at the output I should expect something equal to V or less than V. It can be more than V. The same thing applies to I. If I have a current I over here, the current that should appear at the output of the transmission line should be equal to this I or less than this I. It shouldn't be more than I. If it becomes more than I, then it means we have violated the rule or the law of conservation of energy. So that is why I have delta I over here and also delta V over here. So our task here is to find what delta I is and delta V is. So let's start with what delta V will be. So if I take delta V, that is the voltage. The voltage, for example, if I apply this voltage here, there will be a voltage drop across this arm over here, this L, and a voltage drop across this resistor. So my equation here will be R delta X plus L delta X. Or we'll multiply this I, because this I is going to flow through this and this. So all multiplying I. And I'll have negative here. This negative means that, as I explained earlier, if I apply a voltage here, the voltage that should appear at the output should be less or equal to the voltage that I applied over here. So this negative is explaining how the voltage applied from this end should be less at the output. So that is the reason why we have this negative here, right? So let's see. Delta V will be equal to minus R delta X plus L. The impedance of L, that is inductor, we know to be J omega L delta X, and I have my I over here. From here we can see that delta X is common here, so we can take it out. So I'll have minus R plus J omega L delta X over here, and I'll have my I over here. So to get rid of the transient time effect that will occur in this transmission line, delta X should be 0, right? So if I divide delta V by delta X and I take the limit of delta X to be approaching 0, the result will be R plus J omega L, and I'll have my I over here. So that's the limit of delta X approaching 0 with respect to delta V over delta X. The result will be dV out of dx equals minus R plus J omega L and I. So we can see that this is equation 1. So when we prove for delta V, this is what we should get. Right. Let's look at what delta I will be like. So delta I, for delta I, the current flowing from this side, there will be some current flowing through this capacitor and this conductor over here. So my equation will be G delta X plus C delta X, all multiplying V, because they are across this C, and this G is across this voltage. So that's why I have V here. And I'll bring my negative sign over here because, as I explained earlier, if I apply a certain voltage here, for example, if this is 5, the voltage that should appear at the output should be less than 5 or equal to 5. It shouldn't be more than 5, right? So that is why I have this negative sign over here. So delta I will be equal to minus G delta X. The impedance of capacitor we know to be J omega C. So we have delta X over here and V. Since delta X is common, we will group like terms. So I'll have G plus J omega C delta X V. Again, if you want to take or get rid of the transient time effect over here, to make sure that delta X goes to 0. So taking the limit of delta I over delta X, the limit says that delta X is approaching 0. I'll have minus G plus J omega C over here and V. So the limit of delta I as delta X approaches 0 will be I over dx minus G plus J omega C times V. So we have equation 1 and equation 2. These equations are what we call the telegrapher equation. So if you are asked anywhere to state the telegrapher equation, that is equation 1 and equation 2. Right, so let's continue with our proof. So I had equation 1 to be dV dx minus R plus J omega L multiplying I. That was equation 1, and equation 2 was dI over dx minus G plus J omega C multiplying V. This one was equation 2. So if we double differentiate dV dx, have squared V over dx squared, here will be minus R plus J omega L, and this I will be the I out of dx, right? But now we can see that the I dx is equation 2, so we can substitute equation 2 into this equation over here. So dx squared V over dx squared will be minus R plus J omega L, and the I dx is here, so times minus G plus J omega C times V. Since this is negative, they multiply, they will be positive. So I'll have R J omega L J plus J omega C all times V. So if we say that R plus J omega L is gamma and G plus J omega C is also gamma, we can write that squared V out of the X squared will be gamma multiplying will be gamma squared times V. So looking at this, let's say this is equation A and this is equation B. If we compare equation A and equation B, we can see that gamma squared is equal to R plus J omega L times J plus J omega C. And this gamma is what we called or we term as propagation constant. Propagation constant. So if you want to find propagation constant, that is gamma will be equal to the root of R plus J omega L multiplying G plus J omega C. Also, gamma again, same as having alpha plus J beta, where alpha is attenuation constant and beta is the phase. Right, so let's continue. We come to the conclusion that squared V by the X squared equals to gamma squared V, and this is in terms of voltage. If we want the one in terms of current, we can say that the I squared over the F squared should be equal to gamma squared times I. But then in this section we are going to work with the voltage equation. Later on I'll work with also the current equation and we'll see how both side works. Right, so if I have the squared V where the X squared will be equal to gamma squared V, we know that this is a second order differential equation, and if you want V in terms of phase and time, we will have V plus E minus gamma X plus V minus E gamma X over here, right? So, or we know that gamma was equal to alpha plus J beta, so we can substitute gamma into this equation wherever we see it. So Vxt, we can say that we have V plus E minus alpha plus J beta X plus V minus E alpha plus J beta X. So now this is what we call the incident wave, and this is what we call the reflected wave. So what we mean is that if you have a transmission line like this, and we apply a certain voltage here, the voltage, you have one flowing into the transmission line, and we also have one being reflected. That is what we mean. So this is the V, the voltage that will be incident, and this is the wave that will be reflected if you have this as your transmission line equation in terms of voltage. The same thing also happens if it is a current. Current will also have an incident wave and also a reflected wave. We will look at that as we move on. So in my next video that I'm going to produce, I will use the transmission line in terms of current to also prove some equations or some formulas that we already know and how they came about it. Thank you.